welcome to this course. So it's on AI, ML, and DL. So artificial intelligence, machine learning, deep learning, and bioimage analysis. This is the visual outline of this course. So it will be structured in 5 acts, let's say something like that. So the first chapter would be understanding the basics, then exploring more in depth the machine learning and deep learning techniques, how the models are built, what they do, and so on. Then we will have a look on the pitfalls and the ethical considerations of how we use those models in bioimage analysis. Then we will have a peek at how new chatbots models can be integrated in a bioimage analysis workflow. So basically using LLMs to help us define workflows and even code. And finally, we will conclude by having a small discussion on what is needed to progress in this domain, what we should take home as a message, and also a few, let's say, safeguards that we should put in place when we use AI. So between each of those chapters, we will have a small recap and a short Q&A session. So if you have questions, please wait until we reach these small pauses. So without further ado, let's start with the boring stuff first and have a few definitions out of the way so that we can speak the same language. So AI is a kind of umbrella term right now that is enclosing more and more things as the time passes. So we can think of AI with intelligent appliances, recommendation engines, stock market predictions, and all kinds of machines that are operated by some kind of intelligence. But what is actually AI? So in layman's terms, it's just a technology that produces machines that are trying to mimic what a human will do. So basically doing human-made tasks. So if we focus now on 2 subsets of AI, which are machine learning and deep learning, let's have a look first on the machine learning side of the AI. Machine learning is an algorithm, basically, that learns a pattern on its own in 2 distinct steps. The first step is feature extraction. And the second step is what we call classification or regression. Classification being deciding if an object, an image or whatever belongs to one class or another, and regression is predicting a value. So a numerical value of something, an intensity value, perhaps, something like that. In this case, in this example, we show a photograph of a car, and the model tries to learn if it's a car or not a car. So if we want to get a bit more into the details, machine learning classifier works by trying to predict the probability of an image belonging to a certain class, if we are talking about classifiers. So to do that, we train the model with sample images that have been labeled correctly by a human most of the time. Each training sample is given a class by assigning labels. And in this example, we can use the species of the animal as a label. So for instance, a dog, here the dog has a probability of 1 for the label dog and 0 for all the other species. So it has 0 for goat and 0 for cat. And in the same way, a cat has a probability of 1 for the cat label and 0 for the rest. So once trained, the model will try to predict the correct label of the new images it has never seen before. And it will attribute a weight to each of those specific labels. And the weight that has the highest probability will define the label of the output image. So the class of the animal that is seen right now, with more or less success, as we can see with the goats. So if we translate this to a biological sample, for instance, here a slide scan image, we can use other indicators for labels than the species. And in this case, what we are using are transformations of the original image through various filters. So instead of cat, dog, and goat, each pixel will have a label based on a collection of intensities that are corresponding to the filtered versions of the image through Gaussian filter, variance filter, and so on. And we call these features of an image. So on the other hand, deep learning is a whole different beast, since everything is done actually in just one step. So extraction and classification or regression happens at the same time and takes place in structure that we are calling layers. Each of those layers are composed of multiple neurons or nodes. So just input an image of a car, and then the model outputs directly if it's a car or not. There are no separated processes of extraction and classification. If we look closer at a deep learning model, this is how it looks like. So we have several layers, with each of them having a specific job. They have each of them a specific task, like trying to understand the features of an image and then trying to associate those features to a class or something like that. In short, we could say that the goal of, and the way a deep learning model works is to deconstruct an image into its fundamental elements and combine them back into something that is meaningful. So deep learning models are quite flexible, and with the same architecture of a deep learning model, you can achieve many different outputs, which is quite different from a machine learning model. So for instance, here we can do segmentation or detection, classification with the same deep learning model, in this case, UNet segmentation model. So just a bit of history to understand where all this comes from. Because AI is not something new, actually. It's very old. What makes modern AI different from something that happened in the past is the switch that occurred when we switched from the top-down approach to a bottom-up approach. So I will explain this. The top-down approach consisted of writing every single possible scenario. So basically rules to the system to decide what he does for each case. So obviously, the more complex the problem, the more rules you needed. And this was not something that could scale easily. The apex of this kind of technology was expert systems. And this happened during the 80s and 90s, something like that. But then we reversed this process by trying not to write our rules ourselves, but let the system decide the rules, and by cascading triage and filtering the rules to keep only the rules that are actually meaningful to get the output that we desire. So this is the bottom-up approach or connectionist approach. And this is how machine learning was born. And from machine learning, neural networks, and from neural networks, deep learning. So it's a kind of a Russian doll kind of scheme, if you want. At this point, I think it's just worth mentioning that there are a few different things that needs to be defined. It's a difference between parameters and hyperparameters. Because for a deep learning model, the parameters are basically just the weights. And those are what the model learns on its own. So very large models can have billions of parameters. And those are not to be confused with the hyperparameters, which are actually, think of them like the knobs you can turn to adjust the output the model will give. So we can see them as the settings of a deep learning model. So there are two main families of AI models: the models that are supervised and the models that are unsupervised. Supervised meaning that we show the system what is a good example of output, and unsupervised is a model that will be given some rules, and the model will find alone the best way to fulfill those rules or to achieve the goal that was designed. We will see that this distinction is a bit more blurry than that, but do not memorize this this diagram here. It's just for you to see that there are two big classes of models, mainly. To illustrate a bit the difference here, supervised models will generally perform way better for image-oriented tasks, like segmentation, for instance. We give an example of what we want, and the model tries to adjust its weights towards this example. Unsupervised models like k-means, which is a clustering algorithm, will try to form groups of pixels, here in this case, with similar characteristics, where the model is not guided by any example, but just by the number of classes it has to form. So in this case, just two. So you can see that the k-means model is perhaps less efficient than something that has been trained like a pixel classifier in LabKit in this example. But they still have their use in some other fields that are adjacent to image analysis. So is this relevant, talking about AI in bioimage analysis? Well, if you have just a look here at the very short history of the publication rate of papers about machine learning, neural networks, and so on, you can see that the progress is quite exponential. And obviously, it affects all kinds of fields in science, especially bioimage analysis. And this just stresses the point that the sooner you will educate yourself on this topic, the better. So in bioimage analysis, we can find four main applications of artificial intelligence, which are segmentation, classification, image enhancement or noise reduction, and feature extraction. With all of these quite fundamental to quantify accurately what is an image and what data you can get from this image. So let's just have a small comparison here between the classical approach and machine learning approach for segmentation. So segmentation is done by selecting most of the time by just doing a thresholding. And the problem with this approach is that it introduces bias. There are some reproducibility issues. This approach is also not robust. As soon as the conditions of the image are changing, then the threshold has to be adjusted. So this approach is quite limited. On the contrary, once you train a machine learning model, you will immediately get something that is much more robust, that can be applied to a vaster panel of images and can be reused. So this is also most of the time, depending on how it's done, devoid of reproducibility issues, but not unbiased. But we will see that a bit later. If we talk about complex data sets, for instance, multiplexed slides, where we have dozens of markers at the same time, models like k-means, so unsupervised model, can help make sense of what we are seeing by clustering complex co-occurrences of dyes together to reveal some patterns that were difficult to see if just observed in the classical ways. In the same way, we can also use machine learning as an intermediary step to find some hotspots in images. So we detect cells, for instance, in this example here, but then we use classification, machine learning classification to classify those cells. So it's object classification. We will see this a bit later on. And from those objects, we can define hotspots on the slide, which is something that can be quantified and is very useful. So this is all good, but how do we use machine learning and deep learning in bioimage analysis? What are the tools available to us? So we can distinguish between two categories, again, open source and commercial packages, which is always the case in bioimage analysis. But also, we have to look for packages that work locally and packages that work on the cloud, because some models are very computer intensive and they have been designed from the ground up to not work and not rely on a user's machine, but work on the resources available in the cloud. But that means you need to have the infrastructure and the workflow that works together with the cloud. There are also programming languages that can help here. Instead of having turnkey solutions, you can just write your own scripts. So there are libraries that are available to do that. And most of them have been based on Python, with some of them in Java or MATLAB or R if you want more exotic or specific features. But even then, they are most of the time built on top of Python. So you have a program calling another program just to make everything work. If you want to be on the safe side, just learn Python and stick with this, because you will be able to do most, if not everything, with this. So there is one key advantage of working with a script-based language like Python instead of using applications, that you have access to all the features and all the latest developments for each models or framework that you want to use. So for instance, in this case, the Stardist plugin, which is a deep learning model in Fiji, only allows for analysis on 2D images, while if you use its Python counterpart, you can work on any kind of dataset, 3D, 4D, whatever you want. So there are advantages to using Python. So obviously, there are also some drawbacks. And while programming clearly offers the most versatility and perhaps also the most performance, it comes at the price of ease of use and convenience. So again, this is just a table to show you quickly the differences between those two approaches, but each of them has their own strengths. Commercial solutions also bring AI integrated now in their own software suites. So for instance, here, this is Nikon's NIS program, which includes now segmentation, image enhancement, and all the basics that we have seen integrated into the commercial packages. One key advantage of this, being AI integrated directly in a commercial package, is that it can work together with the image acquisition layer. So this allows for intelligent feedback loops and informing the acquisition with a very robust analysis pipeline behind. Again, the big drawback with commercial solution is the fact that it's closed by nature as well as the costs. So there are advantages, like most of the time it's easy to use, it's intuitive, and the fact that you can combine this with the acquisition, but it's very costly. So let's have a short recap here. The reversal from the top-down bottom approach in AI made possible the advent of ML and DL, so machine learning and deep learning. Machine learning and deep learning are now widely used in many fields, including bioimage analysis. And they are actively improving tasks like segmentation, classification, image enhancement, and pattern discovery. So there's a wide panel of solutions available that can be integrated or programming toolkits. So you can develop your own custom solution. And it can be either local-based or cloud-based. So here I will give you a few minutes to discuss this first segment if you have any questions. So let's switch to machine learning and deep learning techniques to understand how all of this works. So let's start with a nice table, but just forget it. It's just to show you that there is a long list of strategies actually to classify objects. So if we start with machine learning here, we can do two basic classification tasks, which are pixel classification and object classification. And even with pixel and object classification, there are a lot of different strategies available. Pixel classification is assigning a label to each pixel of an image based on the pixel's characteristics. So the intensity, the color, the texture, all the filters you have seen before. The object classification is categorizing an entire object or a region of an image, which is quite different actually, because objects are much more complex and they have diverse sources of data, all sorts of metrics, in addition to their pixel values. So this is a pipeline, a very simple pipeline, where you start from pixels and you turn them into objects, and then you take those objects and you classify those objects. So it's actually a two-step process to classify objects. And tools like, for instance, Elastic have pipelines that are dedicated to do that. And you actually first train a pixel classifier to build objects, and then you train an object classifier from the objects you have created to classify the objects at the end. Here is a detailed example of pixel classification with a protocol like this: image preprocessing to normalize and reduce the noise in the image. Then we do the feature extraction to get the information about the shape, the size, the texture of the image. Then we do the training on the labeled data, and then we apply the classifier to the new images. This is usually how it's done. So let me show you how we do this. So the first thing, if we take a multi-channel images, whether it's fluorescence or bright field, is to separate the channels and to work on each channel at a time. Then we can do other transformations like filtering, scaling, maybe reducing the size of the image can save some time, and we do not need to work at the full resolution of the image. Then we do the feature extraction, which are filters, so convolutions, basically. We can also do some image arithmetics if it helps, but most of the time we just stick with convolutions and some other filters. And we will see that the more features the model has access to, the more precise the prediction can be, as long as the features are properly selected. So some features will actually contribute more than others, and others will just be ignored. So we can just not use them to save time for processing. So now that we have decided what feature we will use, so what filter we will apply to the image, Gaussian, variance, so on, we now have to define some examples for the classifier to be able to work properly. So we will trace examples of pixels belonging to one class or the other. And so here, in this case, the simplest use case is defining between foreground and background. Foreground being the objects that are interesting to us, nuclei, for instance, and background being everything else. So tissue, the real background, so where there is nothing, debris, and so on. Everything will get into the background category. So you have to keep in mind that this is an iterative process that takes several tries and needs to be precise. The user input should be very precise. There are some tricks to enhance the quality of the segmentation here by, for instance, marking clearly the transitions between one class and the other. So in this example, between those cells, you can trace fine lines to decide this is background, and in the cells, you make sure that the foreground is selected. So this way, the difference between what is a cell and what is background is clearly defined. And if you see that the prediction gets worse after getting better a few times, it gets suddenly worse, then either you remove the annotations you've just made, sometimes it's difficult to do depending on the software you use, or you just start over. It's better to have something that is good enough than trying to achieve the perfect result and ruin everything by adding too many annotations. Then, once trained, the model can be used to predict classes of pixels that it has never seen before. So what we see actually as the output is a probability map. So basically a black and white image or grayscale image with the highest intensity being the highest probability. And in most of the software, what we actually see is not the probabilities, but the direct result, which is a segmentation of the probability. Most of the time by a simple Otsu thresholding to keep uh, the highest levels of probability as the result of the threshold. So now, here is an example of object classification. So we have done some kind of pre-processing, thresholding, and so on to create objects, which can also be done by pixel classification, as I just shown here. And then we do feature extraction again, but this time on the objects. So it's not just pixel intensity, but it's size, the average intensity, the texture per object, and not for each pixel. Then we can do the same kind of training by pinpointing here which, in this case, cells are in interface or metaphase. And then we get the classification. So this part here is the object classification, and this part here can be either the pixel classification or something else, manually done, automatically done via classical scripting methods. There are different approaches here to get to this point. If we compare those methods with the traditional approaches, what we can say is that machine learning approaches are rarely necessary on simple use cases. But as soon as the use case becomes a bit more difficult, for instance, like overlapping nuclei here, the classical approach is just not good enough. And it's important to consider the balance between high speed, so the basic methods that are tried and true, and the higher accuracy, but also the higher cost in time and resource to use a machine learning model. So in this case, we have just a classical thresholding, and here we have a LabKit pixel classifier. So you can see the pixel classifier produces a bit better, some better separation between objects. Here is another comparison, just to tell that while classical approaches are have some drawbacks, those are nothing new, and some workarounds have been implemented long ago. So in this example here, a simple size filtering, if you want to segment automatically the leaf here from this image, there is a ruler. You don't want to have the ruler here inside. If you just add another step with size filtering for the particles that are detected, you will just get the object that you want. So you do not need machine learning in this case. But actually, if you train a machine learning model, you will get something that is very similar as a result, but actually is a bit more refined. If you look at the small details, it's a bit closer to the original. So let's switch to deep learning now. Machine learning can help in most use cases, as we've seen, but each model has to be trained for a specific use case. If the pixels vary in intensity, if the image vary in intensity, the pixel classifier, like the simple thresholder, will just fail. So deep learning models are much more resilient to structural changes and have a much more versatile and robust usage. Uh, Here are two examples, Stardist and Cellpose, which are the most well-known deep learning models tools for bioimage analysis. And you can see that in this case, while Stardist is a deep learning model that works well on overlapping cells, Cellpose is a very versatile tool that can be applied to objects that are looking very different, from nuclei to cell outlines or membranes. It will provide good results, even if those images are looking very different. So let's look at what a typical bioimage analysis workflow looks like. You have a sample preparation, image acquisition, pre-processing, and some discovery of the flows of the pre-processing. Then you can add some manual additions to finally get the result you want. So this is more or less the classical approach most of the labs are still using at the moment. As I said, if you try to apply classical approaches, it will fail most of the time. In this example, if you want to identify the round structures here in this image, none of the thresholding methods will work. But the same goes for the machine learning models. And actually, if you use Cellpose, in a few clicks, you get a nice result, even though it wasn't trained on this specific data set. So Cellpose is a deep learning model that is quite versatile, and you can quickly adjust it to your data set. This is a perfect illustration of the power of deep learning models. And another point that is very important, there are some use cases where it's not just difficult, it's actually impossible to do segmentation without relying on deep learning tools, for instance. If you try to do segmentation of glomeruli without deep learning, good luck, because it will be just completely impossible to do. And here is just the comparison between deep learning and the machine learning approach we saw. And so actually, this is not the machine learning, sorry, the classical approach we saw, but you saw that the machine learning was quite close as well. You can see here the distinction, how overlapping cells are handled. It's much better done by Stardist. And if you want to quantify, for instance, the size of the cells, something like a deep learning model is much more suited in this case. So there are some challenges using deep learning, because one of the biggest drawbacks of using deep learning is that it requires a lot of good training data. And by lot, I mean a lot. I mean, Stardist, the first Stardist version took roughly 1,700 carefully annotated images to get decent results. So think about it. You have to manually draw 1,700 images to get something close to what Stardist can provide. And this is just for a model that is not that versatile, actually. It works on round-shaped objects. That's it. If you look for something like cell pose, the first iteration of cell pose needed 70,000 annotated samples. And it's even worse than that, because for some images, you can see that some regions have high variability. That means that they will need more annotations than others. So in this example here, it was some brain slices. And if you want to identify the anatomy, for instance, the eyes, some parts of the brain regions, there are parts that are much more likely to provide bad results if you do not give them enough examples. There are also other challenges with deep learning. One of them is, while it's quite versatile and robust, depends highly on the conditions of the images you provide. A model that has not seen a certain type of data or is not expecting the data you are providing will provide you with just random results. For instance, here Stardist works or is expecting cells or round objects that are roughly of 60 pixel diameter, a diameter of 60 pixels, something like that. If you provide it with something that is larger or smaller, you will get just random results like this. So let's switch gears and speak about another approach that has been enhanced with deep learning. It's image restoration and enhancement. So in this case, there are two approaches here: noise to void, which is an open source algorithm, and you can see the equivalent in the Nikon software, which is called denoise.ai. So there are other ways to improve images. For instance, you can also improve resolution. And so deep learning, in this case here, the super resolution LN model can provide results that are both better, much better, and faster, 90% faster than the SIM counterpart. So deep learning here has a huge edge against classical approaches like the super resolution microscopes. The deep learning models is a very large family. In this case, if you just want to have a peek of what are all the subcategories for just single image super resolution, here is how it looks like. So this is just to give you a sense of scale. There are lots and lots of models. And of course, the same applies to every other kind of tasks like segmentation, like classification, and so on. So you just have to keep in mind that it's perhaps a good idea to know the types of tasks that are available, but then do not focus on a specific model because there are dozens of them. So since we are in the image restoration and enhancement section, can we say that deconvolution is useless now? Well, it's not dead, actually, because there is now deep learning assisted deconvolution. In this case, it's called RLN for neural network. And you can see the difference between what a wide field image, the classical deconvolution, the Leica Thunders approach looks like, and the neural network assisted deconvolution, which provides the best result, even better than confocal here, from just the wide field original image. So it's still deconvolution, but it's AI assisted deconvolution, which is now the new normal. So like for deep learning, for machine learning, deep learning can also be used using a lot of applications that are either self-contained within an app like Fiji or iElastic, or via scripts. For instance, you have the BioIMage group of scripts, the zero cost deep learning for microscopy ensemble of scripts. And you have also Napari, for instance, which is a GUI that sits on top of Python that is trying to bridge a bit those two worlds together by bringing a graphical user interface, but with the freedom of working with programming scripts, so Python-based scripts. But the knowledge requirements are higher than with self-contained apps, and of course, with machine learning. So you can also find deep learning directly in commercial packages. And each of the solution, whether it's commercial or not, will need time to learn. So you must think quite carefully before investing too much time and energy in one of those approach, because you might not be able to access those software later or just afford them because they are very expensive. So that's why it's probably always the best idea to work with open source solutions. So let's talk a bit now of how a deep learning model is trained. There are two main strategies: from scratch or via transfer learning. So training from scratch requires a lot of training data, but provides a very tailored result. So something that is really designed for your use case. But again, it requires a huge amount of data, as we've seen for cell pose, tens of thousands of images annotated. Transfer learning, on the other hand, starts with something that is already working, a trained model, but then it retrains it. It just adds more examples to guide the model towards something that is more specific to what you are doing. So it's faster, it's less demanding, but it's quite difficult to steer a model away from what it has been trained on. So you cannot start with something that is completely different and expect good results if you are trying to apply this model on something that is not what the model was trained on at the base. And it's also a bit more limited by those same original characteristics. If the model has some limitations, you will get the same. You cannot change them. So the fuel to train models are annotated data, which we also call ground truth images. And ground truth images can be obtained via various means, like human experts, manually drawing the rise on the images, or any kind of segmentation that has been created afterwards. So there is manual labeling or automated labeling, plus an additional step of curation, so checking if the automated labeling has been done correctly. And thinking about this, you can see here some examples. So manually labeling is really tracing the regions. Automated labeling is just using a kind of segmentation and of thresholding, for instance, and saying what is above the threshold will be used as the ground truth annotation, and what is below will be excluded. So, but actually, when you do that, you are just training a model to act as a thresholder. So up until now, we spoke a lot about deep learning models and neural networks, but I didn't get too deep inside the model, no pun intended. So let's have a look at the core of the deep learning model. It's actually a network that is composed of interconnected neurons arranged as layers, so as I said, and each layer having a specific task that goes in increased degrees of complexity. So it starts by identifying edges in images, then combinations of edges, then features, and so on. So if you have a look at this example here, look at the face, it will start to see the contours and then associate the contours into features, face features. Is it an eye? Is it a mouth? And so on. And then try to recognize what type of eyes, what type of mouth, and so on, to finally get the output, in this case, a famous actress. So we can say that a deep learning model is something that really tries to mimic how the vision system, the human vision system works. So as I said, each layer is composed of structures that are named artificial neurons that act like biological neurons. They have an activation function quite similar to the action potential of biological neurons. And these artificial neurons are have arranged are arranged in layers with two main functions, which are extract features and classify. And I will repeat this again and again, but it's to make sure you understand this. And at this stage, it's really trying to mimic biological functions. So you get two examples here of artificial neurons and their activation functions, and how they are arranged into layers. So here, CNN, convolution neural network. We will see that in a moment. So now let's try to look at the most common deep learning architecture to make a bit some sense of all those layer stuff, diagrams that you must have seen, because it's sometimes not very clear what they are doing. So you can think of the CNN, the convolutional neural network, as the ancestor of most of the models that are used in bioimage analysis. It's a classifier that is used in tasks like predicting if cells are alive or dead, if some growth of an organoid has reached a certain stage or not, and so on. The fact is that it doesn't retain any spatial information because it's really, at the essence, a simple classifier. It turns pixels into a class. That's it. So it cannot be used for segmentation here. So CNN, image classification, object detection. Is the object present or not in an image? You can use it as a feature extractor if you rely just on the first part of the model, but there is no spatial information. So to address this issue, we have now the fully convolutional network, FCN. So it's a twist on the CNN, Because at the end of the model, instead of having just a class as a result, you keep the spatial information so you can output an image, because you have a class for each of the pixels, actually. So that allows for semantic segmentation, pixel-wide classification, and spatial information is preserved. Next is the UNet, and all the cousins, sisters, brothers of this network, because there are a lot of them. But the UNet has something that is quite peculiar in the fact that it's not only shaped as a U, but it has what is called skip connections. Because up until now, you went through the model by following the path of the layers. So from the input to the output. But with the skipped connections, you have actually paths that allows for direct comparison between different um, levels of layers. So at each step, you can compare how the image has been deconstructed and how it has been reconstructed. This is what makes the UNet very unique and allows it to be also very versatile. Um, for instance, it can be used for denoising, segmentation, classification. You can almost all of the tasks can be done with the UNet because of this feature here. And without going too much into the complex parts of it, the way you progress here through any kind of neural network is by decreasing the size of the image, the dimension of the image, by increasing the number of features. So that's why you can see those thin lines, which are the XY, think of that as the XY dimensions of an image, which is getting smaller and smaller and smaller. But the number of features, or the stack of features detected, is getting bigger and bigger. And then from those features, you try to reconstruct and expand again the image to make it look as the desired output. So in this example here, the UNet is the care model here and provides an excellent denoising result. Stardist is a UNet model. So another thing to consider is the time dimension, because life is not something that is static, it's moving all the time. The studying of time series is something that is essential in biology. And for this, we have RNNs, which are recurrent neural networks. And one of the main applications of those RNNs is to predict frames in a time series. So either frames between a time series or frames that will occur after a certain amount of time. It can also be used to interpolate Z stacks, for instance. It's very good at predicting missing parts. If you have 3 or 4 slices in a Z stack, you can turn it into 100 of slices, if this is something that can be useful for you. Then we have one of the most strange neural networks, I think, which are the GANs. And GANs stands for Generative Adversarial Networks. Why adversarial? It's because you are actually having 2 different models fighting each other. You have your training set here. So examples of images annotated here, and something that is called a generator. So this is one part, one half of the model, which starts from random noise, and this is important. You will see that later. And it will create something completely random, a fake image. And then you have the other half, which is the discriminator, that will try to define if what he sees is actually a real image or a fake image. The real image or the fake image being the output that you desire. So that means you can, for instance, give it wide field microscopy image here, and here what you expect as a result is, let's say, a fluorescent channel. So you give it DIC image, and you want as an output blue labeled DAPI nuclei. This will try to generate those nuclei randomly, and this will decide if what it sees is actually the nuclei corresponding to this image or something that is fake. So you have constantly those two models working against each other. But at the end, what you can get is something that is able to generate a modality or a channel that doesn't exist. So it's with this kind of neural network, we are entering the generative machine learning, generative artificial intelligence. Then there are other more exotic models like autoencoders, which look pointless actually if you try to understand how they work, because they are simply destroying the image and reconstructing it. But they have been trained with degraded images and as a result, nicer images. So what they are specialized to is trying to recreate proper, nice images from images with artifacts, all kinds of artifacts. It can be noise, but it can also be stripes, any kind of artifacts proper to the modality of the acquisition. So, for instance, if it's tomography, you have several kinds of stripes. If you have light sheet microscopy, again, you have uneven illuminations and things like that. This will be corrected using autoencoders. So a bit previously, I defined two main categories of models based on how they were trained, supervised or unsupervised. And I told you the line is actually a bit more blurred than that. So actually, the supervision level can be either complete, absent, or partial. Uh, so the other factor you can also look at is at which point during the training we tell the model if what he is predicting is actually right or wrong. So this gives you a matrix of learning from supervised and transfer learning to reinforcement learning, semi-supervised, self-supervised, and completely unsupervised learning. And for each of those models, you have nice applications. For instance, let me just see here, because I don't see quite well on my slide, sorry. You can think of reinforcement learning, because this is something that is not well known for semi-automated acquisition. You can tell the model what we want is actually having cells reach a certain level of confluency. And we set this as a rule. And it has nothing else. So it knows what a cell is because it has some previous knowledge, but it doesn't know when the confluence happens. So you can use reinforcement learning with this by gratifying the model as soon as it detects correctly this stage of the cell development, or punishing it. So this happens later, actually, in the time of training. So let me give you a few more examples here about transfer learning, because I think cell pose is something that you should learn to use. So here, this is an image that is actually not showing nuclei. Cell pose has been trained to detect cells and nuclei, but this is not an image of cells or nuclei. It's a convalia sample. So if you try it with the default nuclei model, you will get a decent result, but there will be some parts that are missing. And with just a few successive iterations here, we can train the model to learn how to detect those missing cells, or which are not cells, but we just give it a few examples. And so we have 6 consecutive versions of the model, and the 6th one is the one that succeeds every time. So it's actually much faster to work this way than to train 70,000 of images. It's just another visualization of this example with previously 34 detected structures here, and correctly now 46, so all of them. So let's again recap a bit what you've seen until now. We have seen that the techniques of machine learning and deep learning differ between the different types of models we have. We have seen that we have models that can be trained by supervision and others not. We have seen that most of the deep learning model stem from convolution neural networks, and one of the most used of them is the UNet architecture. And again, we have already said that, but most of the use cases are classification, segmentation, image restoration, and image enhancement. This was the biggest part here, the model architecture, how they work, and so on. Here, I will go a bit faster since we are now talking about something that is not important at all. It's ethical considerations and pitfalls. No, seriously. There are some stuff that you should be concerned about. And the first thing with using machine learning and deep learning are the inherent variability of training. So there are reproducibility issues. The first thing is that when you work with artificial intelligence, whether it's deep learning or machine learning, it may be trivial But biologists tend to not annotate what they do. The lab part is very well documented, but for the training part, for instance, the scribbles I just shown you on how to train a machine learning model, this completely disappears. In most of the programs used, it's not even an option to save them, but it's actually very important to know how this model, this pixel classifier, for instance, has been trained. What were the examples used to teach the model? And even with just using the model, there can be very high variability. Think about it. Changes in data used for training. If someone else uses another data set to train the same model with the same conditions, you will get a different result. If you use different model settings, so hyperparameters, you will get a different result. Some models have inherent randomness. They are just built with randomness inside. So think of the GANs model before, because they start with random noise to produce the image. Randomness is the essence of those models. And again, repeated model usage without noting any changes you have made at the time can also lead to different results. There are also software and hardware variations. If you work on a Mac or a PC, if you work with different versions of the software, and even the same algorithms can produce inconsistent results, just depending on how they run. So let's address the built-in variability of the models. So I told you before that to train a machine learning model, you try to minimize what is called the loss function. You want this loss function to lead to the smallest difference between the prediction and the reality. But if you think about this here, if you have just two features, trying to find the best weight for the feature can lead to local minima. If you start here and you go into this direction to find the smallest solution, so to the loss function, you will end up here. But the actual minima is there. So how do you address this problem? Well, instead of starting from here each of the time, you start somewhere randomly. This is what is shown here. You start with initial model weights completely randomly. If you set all the weights to 0, the model actually never learns anything. You will just never get any prediction. And if you set the random seeds of the model, the term here that is coined is the seed, between an interval that is around the variance, then you will get something that is beginning to get something quite efficient. After a few iterations, the model will quickly minimize its loss function correctly. So that's why you need to have a random start, a random value initialization. If not, the model will just never learn. But this introduces surprising results. If you train 2 times the same model with the same data set, you will not get the same result. This is called stochastic learning, actually. And you can prove this, so I will quickly skip through this, but this is a code example just to show the accuracy here of the test. And if you train several times the same model, you will get several different results. And in this case, it's not for machine learning, but for deep learning, because you have the same concept to avoid issues like overfitting. So in this case, it's not learning, but it's actually learning too well. In the sense, it will only identify the original data set and not the rest at all. So in this case, what you do is you turn off randomly parts of the model, some layers, some nodes. This is the dropout level. And again, this is the same as for the machine learning approach. It's random. Otherwise, you do not get consistent results. But consistent doesn't mean always the same. It's just around the same ballpark. That's it. Yeah. It's really done to mitigate the overfitting, but again, it introduces randomness. Now, let's talk a bit about biases. So the quantity of training data matters. As I told you before, there are some areas in those images that need more examples to be accurately segmented. Here you can see the difference if you try to segment the same object with 36,000 examples of ground truth images and 135,000 here. So the difference is actually quite visible. But not only the quantity of the data matters, also the quality of the data. And this addresses the problem that is called dataset shift. So if you try to use a model of a certain type of data, but only train on a subset of this data, you will have what is called a covariate shift issue. So that means, for instance, you try to identify dead and living cells, but you only give 90% of your data is annotated dead cells. Of course, you will introduce some bias because the objects will not look the same. Dead cells are round, the other cells are more diversely shaped. If the balance between the classes is offset, then here it's the same. Even though you get perfectly nice examples, if they are not evenly distributed in your training set, you will introduce a shift. So this is the prior probability shift. It assumes that if you have more of one type of cells in your training set, you will get the same balance in the output, which is not always the case. And then there is the concept shift, is that you're just trying to use the model, something that is not meant for. It's the same objects that you are trying to identify, for instance, cells, but the model has been trained on fluorescence images and you are giving it a bright field image, DIC image. Of course, the model will provide very random results. And those are biases that can influence the results. Now, there are other and worse types of biases. And those are much more difficult to mitigate because they are depending on the experts that are annotating the images. The ground truth images have to be, at some point, either directly annotated or curated by an expert. And as you can see in this example, there's a high variability between different observers to annotate the same sample. Those are the same samples that have been annotated by 18 different observers and the repartition between the classes. And you can see how widely different they are. So to get consistent results here, The strategy is to try to get not one expert, but multiple of them to at least alleviate for this difference here. And ideally, to train not one model, but multiple models, and then train a consensus model trained on different models that were trained by different experts. So this is how you can mitigate the variability that is inherent from the experts. And this is called a consensus ensemble model, which are working the best. But this requires a lot of time, energy, and human resource, which is not always available. Then, if we take a step back, we can also see biases everywhere, basically, not only in the model training, but also in the usage of the model. And beginning with the data availability, the dataset curation are introducing bias. If the biologist decides to choose this species, this batch of cells or another, this is already introducing a bias. Then how the model are applied on which data and so on and so on. So there are a lot of sources of biases in machine learning, and it can lead to dramatic conclusions because if we look at the biases from the previous pathology experts, they can also be found in the same way, in the same proportions with clinicians on the operating table when they use AI tool to decide whether they have to cut or not, to leave or not, some organs or not. There is a study here that you can read if you want to, and it's quite chilling, actually. So let's switch to something a bit more fun, at least, if not very positive. But there is also a lack of understanding of how the model works, and the model, the tool itself, the model enclosed as an application, if you want. If you take, for instance, this very nice tool, which is called SAM, so Segment Anything Model, was developed by Facebook, actually, so Meta, to identify objects in vacation pictures, but it works well on any type of images by focusing on what is standing out of an image. You just draw a square and it automatically defines an area. So it works very well. The problem is that this tool here has a high degree of variability, depending on the viewer level. Because if you zoom in or zoom out, what you will give is a different screenshot, if you want, to work with for the model, and you will get different types of area. So if you, again, try to quantify something, which is the goal of bioimage analysis, you will get quite different results depending on the zoom level you are using. So if you're not aware of that, you might not be able to reproduce some results. There are other types of limitations for each of the models. So, for instance, in this case, you try to apply the same models, so random forests, k-means, and thresholding, for instance. So those are machine learning models, and this is just the classical approach on different data types. Images that are high quality, that have some noise, or that have some kind of any kind of alteration. here. And you can see that the random forest model, we completely ignore if the image is noisy or not. It's not dependent on noise. You get approximately the same result as a high quality input image. But as soon as you use k-means on a noisy image, the result will be greatly degraded. But if you look on something where there are some missing wedges, then the random forest model completely falls apart, while the k-means is good. So you need to understand when to use one model and when not to use it, because otherwise you will get into trouble quickly. Another type of misuse is trying to hack a model. So I actually did this, and in this case, it worked more or less. But as I said, Stardist is trying to identify round or shaped structures. So you can trick it to detect muscular fibers here, uh, which works quite well, but we are actually in the territory of trying to work with the wrong structures and even perhaps with the wrong modality, because you have to convert a color image, so coded in RGB, into something that is black and white. It's starting to get a bit shady here. But yeah, you have to really understand the model you are using to make the best use of them. Then I will skip a bit faster on this part just to show you here on this slide that the package version and hardware differences have also a role to play. If we try to see if there are differences between the same libraries but at different versions, or the same libraries with the same version on different hardware, you can see there are some differences in the results. So even then, trying to keep everything the same is very hard, and there is a probability of having a difficult time to reproduce your experiments when using machine learning. So the key to avoid any kind of reproducibility issue is to try to freeze everything the most you can. So by starting by having always the same OS, the same packages, and try perhaps to virtualize everything into a container. And even then, run this container on the same virtual machine to keep everything the same as possible across time, which is something that you cannot honestly expect from any biologist to do. So before ending this section here, just having a look at the bigger picture, while AI usage is soaring, and with good reason, it's really critical to ensure that every user and developer knows how their tools work and their shortcomings. From data acquisition, even from data creation, image processing, image analysis, every step needs to be carefully considered to ensure really minimal amount of biases and randomness in the pipeline. So this makes AI usage quite hazardous, especially with the continued increase of models available and technologies available. And it's very hard for a single individual to keep track of everything that is going on and keep the level of expertise needed to work correctly. So again, a small recap here. The take-home message here to ensure proper usage of AI is to try to prioritize reproducibility. Try to make sure that your model works with the data you are trying to work with, reduce as much as possible, the biases that you may or may not know you are introducing, and also try to be consistent with the hardware you are working with. Okay, so now that we have seen ethics and good practices and they are out of the way, it's time to look for something a bit more fun. And why not try to talk to our images? Yes, because we can do that. So LLMs, they are what is quite hot these days, chatbots, your chat GPTs, Claudes, and so on, can be actually used to develop scripts for bioimage analysis. So it's another form of machine learning because generative AI is trying to produce something out of nothing, actually, just a set of instructions. And one good example is GitHub Copilot. This is how it works. You try to start a script, and then Copilot will try to autocomplete the sample. So here it's Python code, and it will even suggest the next code lines as you type. So this is quite nice. You type definition, this is a function that does this, and then immediately it will provide the next step, which is very useful. You describe what you want to do. You can even just comment. The next function I want to do is a function that counts objects on the red channel, something like that. And immediately, the next step will be written by GitHub Copilot. It works quite well. Here is an example to bioimage analysis, sort of. Try to check if you can segment an image here. But it works very well with Python. It can also work a bit with Fiji macro scripts and so on, but the accuracy is not that great because I think there are less examples with the macro language and other exotic languages. If you are not used to work with tools like Visual Studio Code and working with Copilot and things like that, there is a new plugin for Napari. So think of Napari like an ImageJ version in Python. It's more or less like this right now. So it's a graphical user interface, and it has now, I don't know, roughly 400 plugins. So it's growing very fast, and it allows to manipulate the images and do basic stuff. And you have a plugin which is called Omega, where you can tie your ChatGPT account or Claude or whatever to it, and it will suggest the next step for the bioimage analysis. So in its most basic form, it's just a chatbot specialized in bioimage analysis. And it will give you some example of codes that you can use and so on. But it can also be integrated into a code editor and even produce whole pipelines if you want to. So this is quite nice. So here you have a live example where you described in a prompt. So you really type in plain language what you want to do, and then the chatbot will come up with a plan, and it will input the plan and do the stuff to analyze everything. So I will not go up to the end here because it's a bit long. But let's just say that you have Omega, and there is another tool here, which is called Bioimage IO chatbot, that goes even further, because this one can also interface with your equipment to drive the acquisition of data. So you have everything that can be automated, and you talk to your chatbot to say, acquire 10 images, analyze those images. If one of them is nice, go back to its position and acquire at a higher resolution, things like that. So without any programming language, without anything. So it's coming now very nicely. And there is even a webinar that is now available from Globias online if you are interested in this, that shows how this works. So is this really something that is worth considering? Well, actually, yes, because it's lowering the barrier of entry for image analysis. Because with the wealth of tools available, it's becoming more and more complex to decide what to do. And so a biologist can now have more insights on what is a good workflow for bioimage analysis by just asking with plain language here and get executable code directly out of it. So this is something that I just tried. I gave it this image. I asked for something, and then I got this result, and without doing anything in between. So is this actually quantifiable? Can you measure the effects of LLM usage? Sort of, if you look for surveys, you can see that for developers, using Copilot has increased their productivity by 88%, focus by 74%, and so on. So I would not rely too much on this, but what I would keep as a message is that it really helps in avoiding common mistakes, small typos, and so on, and focus on really what's important. So the real pipeline, the real workflow, and not focus on the details on how to implement this workflow. Also, there are some risks associated to that. The fact that the code that is generated by those tools can be unfamiliar. So researchers might not know really what they are doing. Even if the thing works really, if you just have a look here how some common Fiji commands are translated into Python. If I ask to do a Gaussian blur, a thresholding, and then a watershed, those first two commands are 2 lines, but then it's a whole spaghetti code paragraph for the watershed. So if you're not savvy enough in Python, you might not know if there is something going wrong here. And the different models you are using for this are also affecting the results. Currently, I would suggest to use Claude. Claude 3.5 is the best, but it's not the best for everything. here is a matrix. Here is testing various models for different tasks here and checking if the result is appropriate or not. And you can see that some models are very bad at everything. Some models are good for most of the things, but not all of them. So depending on what you are asking, it might end up with a good or a very bad solution. And another thing that you can you have to pay attention to is if you rely too much on AI generated code, it might be very difficult to spot common mistakes here. For instance, something that is just an equality or greater than sign here is something that is very difficult to spot, and the code will not crash. It will provide some results. If you are not looking at this and understanding what it does, then you will completely miss the problem here. And then there is something a bit funny, is that who owns the code? Here, I just tried to create a QPass script by typing here and the description, so in a comment. So this is sample code showing how to automate annotation created in QPass. Then the next line suggested was author. Usually, when you begin a script, you get the author, you mentioned the author, it automatically suggested Pete Bankhead, which is who is the developer of QPass. But he's nowhere to be seen here. So why does it suggest Pete Bankhead? So this is quite strange. That means it has been trained on data coming from the source code from QPass and examples that Pete wrote. But actually what I'm outputting here is not something that Pete wrote. So who is the author? Do I have the right to use this? So I asked this question to some experts, and they told me that if the training has been done on code that has been willingly shared, then there is no issue because the code was shared at the beginning. So it's open source, it's okay. But otherwise, sometimes you can end up with reusing something that is not open source. So be aware of that. So a quick recap here. Using LLMs is really nice to start coding without knowledge, to improve efficiency in analysis and speed of defining workflow, but there are risks, privacy concerns, building some kind of dependence on those tools, and maybe also cost implications because using those models is not free. Some of them are free, but they are bad. The good models are expensive to use. So I will skip the pause here since the time is quite advanced here and quickly skip to the conclusion, which is quite fast. So we have to follow the AI trend because it provides huge improvements in accuracy, ease of use, speed, and accessibility. So you can't deny those advantages there. But that being said, you really need to understand that you have some responsibility. Using AI means watching for biases, reproducibility issues, loss of understanding of what you are actually doing, the lack of validation if you do not know how to make sure that the results that you obtain are valid, as well as a growing pile of ethical considerations and questions. So if you have just one take-home message is that while maintaining human oversight is essential, you can use AI as a tool to augment what you are doing, but not replace it. So if you want to use it, ask yourself, am I using this with some skepticism? Is this the appropriate tool? Is this maybe something simpler to use before jumping directly into AI? Do I understand what I'm using? And how can I make sure that my results are actually correct? So what are the good practices? Well, here, what you should do is, first of all, really keep learning about this. Look for education, for tutorials, webinars. There are a lot of them right now. Ask experts before doing something not knowing, because it looks easy to do, but it actually has huge implications. And try to attend events and workshops if possible. And before concluding, a last peek here that maybe is the good news here is that the new trend is towards explainable AI. So considering AI not as a black box, but something that gives hints on why it has decided these objects belong to this class and not this other class, by giving graphical feedback of maybe maps, heat maps, or probabilities, or confidence intervals, and so on. If you have now this trend that is growing, then it may be much more attainable to use this tool as everyday tools here. So to recap everything here, AI is a huge improvement in efficiency, and there are risks. So you have to really balance those two, innovation against scientific rigor. So thank you for listening, because it was quite long. And if you have another questions, don't hesitate. The illustrations were made with Midjourney, if you were wondering.